In this video, we're going to analyze one dynamic property of cascodes, which will explain why cascode amplifiers often have wide bandwidths. I've included a cascode amplifier on this slide, along with a small signal dynamic model that represents it. As a reminder, we analyze cascodes by pretending that they're two-stage amplifiers. The first stage is a common emitter, and it's loaded by a second stage, a common base. Here are the relevant lab approximations for the amplifier parameters of these stages. And this is for DC amplifiers, that's not including the behavior of the CPI and CMU. This is all nice, but it isn't new. However, I wanted to retread this terrain so I could reveal a neat detail. The gain from the input to the M node is pretty close to 1. It's given by the gain of the first stage times the interstage loading. The gain of the first stage is GM-RO1. The interstage loading, if we say that 1 over GM2 is much smaller than RO1, cancels out the RO1 term and the GM1 term. So you have a gain of about -1 from Vin to VM. That means the VM node doesn't move much, and as a result, CMU1 doesn't get heavily Millerized. The swing across CMU1 is only twice as large as it would be if you were just moving Vin on its own. So because CMU1 doesn't see a big Miller effect, it winds up that its open circuit time constant is pretty small. The other caps in the cascode have fairly small open circuit time constants too. For instance, CPI2 up here is attached to the input of the common base amplifier this way. So if I replace this with a test voltage source, I'm directly controlling my VBE2 voltage, which means CPI2 sees the 1 over GM input impedance of the common base. CPI1 sees RS in parallel with RPI1, which is probably going to be at least moderately large, because you can't get smaller than RPI1. And CMU2 sees the collector resistance in parallel with the big impedance you see looking down into a common base or a cascode, this sort of left-right pattern here. So basically it sees the collector resistance. So we went through sort of a quick approximation of all 4 of these open circuit time constants, and you'll do a detailed calculation in one of your labs. And we have to go through all 4 of the caps in a cascode because all of them have open circuit time constants that are pretty similar and quite small. So that's cool, it means cascodes are fast amplifiers, but it's also unusual. Most amplifiers are dominated by 1 open circuit time constant. And in fact that behavior is so common and useful that designers often introduce capacitors to create a big open circuit time constant, which is called dominant pole compensation. More on that later. But because most amplifiers have 1 dominant open circuit time constant, if you know what cap causes it, you can just find that open circuit time constant and ignore all the rest of them. So here in a cascode we have to go through the exercise of finding 4 open circuit time constants. In many amplifiers you can get away with just finding 1. So in summary, cascodes are much faster than common emitters because CMU1 is not Millerized. Other caps in the cascode also see low impedances.